The moment I connected that first LED to my homemade electromagnetic field detector and saw it blink for the first time, I knew there was no going back. But nothing, absolutely nothing, prepared me for what happened when I compared my own electromagnetic signature to other people. What I discovered that night changed everything. Welcome back to part 2 of our Biofield scanner series. I'm Sarah, and if you watched part 1, you know I went from complete electronics novice to building functional biofield detection devices in just 6 months. Today, I'm going to show you exactly how to build your first electromagnetic field detector, and I'm going to share the mind-blowing results from my first real-world tests. But first, let me tell you about the moment that made this entire journey worth it. After weeks of studying schematics and learning about components, I finally had all the parts laid out on my kitchen table. A CD40 17-decade counter, some LEDs, a few resistors, a breadboard, and a 9-volt battery. It looked like nothing special, just random electronic components scattered across my table. I was following the schematic I'd found in my research, carefully connecting each wire according to the diagram. The CD4017 is the heart of this detector. It's a CMOS integrated circuit with 10 decoded outputs, and when you connect an antenna to its clock input, something magical happens. The antenna picks up variations in local electric fields, and these variations trigger the logic input of the chip. Here's how it works, and this is where it gets fascinating. When electromagnetic fields fluctuate around the antenna, they induce small voltages that provide clock pulses to the CD4017. The chip counts these pulses and advances through its outputs sequentially. If you connect LEDs to these outputs, they light up in sequence, and the speed of the sequence indicates the strength or activity level of the electromagnetic environment. The components you need are incredibly simple and inexpensive. The CD40 17-decade counter costs about $2. You need a handful of LEDs, maybe 50 cents each. Some current limiting resistors, a few cents each. A breadboard for assembly, about $5. A 9-volt battery and connector, maybe $3 total. The antenna is just a piece of insulated wire, basically free. The entire detector costs less than $15 to build. Building it is straightforward once you understand the connections. The CD4017 has 16 pins, and each one has a specific function. Pin 16 connects to positive power, pin 8 connects to ground. Pin 14 is the clock input where we connect our antenna. Pin 15 is the master reset, which we tie to ground to enable normal operation. Pin 13 is clock inhibit, also tied to ground. The magic happens at the output pins. Pins 3, 2, 4, 7, 10, 1, 5, 6, 9, and 11 are the 10 decoded outputs. As the chip receives clock pulses from electromagnetic activity picked up by the antenna, it advances through these outputs in sequence. Connect an LED with a current limiting resistor to any of these outputs, and you get a visual indication of electromagnetic field activity. I started with just one LED connected to output 0. This creates a blinking effect where the LED flashes at 1/10 the frequency of the incoming electromagnetic pulses. If you're detecting 60 Hz fields from household wiring, you get a 6 Hz blink rate, which is perfect for visual observation. The moment I connected the battery and saw that first LED blink, I felt like I'd unlocked a secret door to an invisible world. But the real revelation came when I started testing it around different environments and different people. First, I established a baseline by taking the detector to an area with minimal electromagnetic interference. In my backyard, away from power lines and electronic devices, the LED barely flickered. This became my reference point for a quiet electromagnetic environment. Then I started testing near known EMF sources. Near my Wi-Fi router, the LED blinked rapidly and consistently. Near my microwave oven when it was running, the activity was intense and chaotic. My cell phone during an active call created distinct patterns of electromagnetic activity. Each device had its own unique electromagnetic signature. But here's where things got weird, and I mean really weird. When I held the detector near my own hand, I saw consistent, low level activity that wasn't present when I held it near inanimate objects of similar size. At first, I thought it might be static electricity or some artifact of my body heat affecting the electronics. So I did what any curious person would do. I asked my roommate Jake to participate in an experiment. Jake was skeptical about the whole project, constantly joking that I was building ghost hunting equipment and wasting my time on pseudoscience. The results shocked both of us. When I held the detector near Jake's hand at the same distance I'd tested my own, the electromagnetic activity was dramatically different. Where my hand seemed to generate subtle but consistent electromagnetic variations, Jake's hand produced almost no detectable activity beyond the baseline readings I'd measured near inanimate objects. We repeated the test multiple times, switching positions, testing different parts of our bodies, ensuring the detector wasn't malfunctioning. The results were consistent. My body seemed to generate significantly more detectable electromagnetic activity than Jake's body, even though we're similar in size and age. This discovery led me down an incredible research rabbit hole. I started finding scientific studies suggesting that individuals do indeed vary in their electromagnetic signatures. Some research indicates that factors like hydration levels, emotional state, physical health, and even personality traits might influence the electromagnetic fields generated by living organisms. But the breakthrough that really convinced me this technology was worth pursuing came during an accidental discovery. I was testing the detector one evening when I was feeling particularly stressed about a work deadline. The electromagnetic readings around my hands were noticeably higher than they'd been during previous relaxed testing sessions. Curious, I decided to try a simple meditation exercise. I sat quietly, focused on my breathing, and deliberately tried to relax my mind and body. As I calmed down, I watched the electromagnetic activity around my hands decrease in real time. It was like watching a direct biofeedback display of my nervous system state. This observation aligned perfectly with research I'd been reading about Bofield phenomena. Some studies suggest that electromagnetic activity around living organisms can be influenced by physiological and psychological states. Stress, emotional arousal, and mental activity might all contribute to detectable changes in Bofield strength or activity. The more I experimented with the detector, the more patterns I started noticing. Different people produced different electromagnetic signatures. The same person produced different signatures in different emotional or physical states. Certain environments seemed to amplify or dampen these effects. I started testing friends and family members, always with their informed consent, and always explaining that this was an educational project, not a medical device. The individual variations were remarkable. Some people produced strong, easily detectable electromagnetic activity. Others generated readings barely above background levels. What fascinated me most was discovering that the people who generated the strongest electromagnetic signatures were often individuals who described themselves as sensitive to electromagnetic environments. They were the people who reported feeling drained around certain electronic devices, or who claimed they could sense when their cell phone was about to ring. Could it be that electromagnetic sensitivity isn't just psychological, but reflects actual individual differences in biofield generation or electromagnetic interaction? The implications were staggering, and I knew I was just scratching the surface. The detector I built was crude but functional. For under $15 and a few hours of assembly time, I had created a device that could detect and visualize electromagnetic activity that's completely invisible to our normal senses. But I also knew this was just the beginning. In part 3, I'm going to show you how to build the second component of our Biofield scanner, a galvanic skin response sensor that measures the electrical conductance of your skin. This sensor reveals how your nervous system responds to emotional and cognitive stimuli in real time, and when combined with the electromagnetic field detector, creates a complete biofield detection system. But more importantly, I'm going to share the shocking discovery I made when I used both detectors simultaneously during a controlled experiment with emotional stimuli. The correlation between electromagnetic field changes and skin conductance changes was so strong and so consistent that it forced me to completely reconsider what we might be detecting when we measure biofield phenomena. The moment when everything clicked together is coming in part 3, and I guarantee it will change how you think about the invisible energy systems operating in and around your body every single day.